All right, so now that we've learned let me quickly go back here, the hydrostatic pressure formula, also known as the absolute pressure formula. What's interesting about this formula is it's assuming that zero pressure means that there's absolutely nothing. So there's no molecules, nothing. That's how we define zero in this formula. That's why it's called absolute pressure. Gauge pressure is redefining what your zero means. So basically we're getting rid of this P naught term, this pressure at the surface of the liquid. We're redefining the pressure to be wow, lost my train of thought. We're redefining what the pressure is as if the pressure at the surface of the liquid was the zero, right? So this would basically what this just ends up being is that the gauge pressure is absolute pressure, the hydrostatic pressure formula, minus P naught. So gauge pressure is just rho GH. So some implications of the hydrostatic pressure formula, the absolute pressure formula. So looking at this situation, so what's depicted here is a container and all this is connected. Alright, so it's kind of a funky shape, but that's okay. Both sides of the container are open up to the atmosphere, so there's not closed lids. The question here is, we saw from the formula that the pressure of liquid depends on the depth and what the pressure is at the surface of the liquid. So the question is this situation possible? Right, so the situation here would be that the fluid has two different heights. Let me know what you think. So the answer here is no, with an asterisk. So assuming that this fluid, this water, is not moving, but still, then this is not possible. Right? So why is this the case? So if these have different depths, that means that at, let's say, the bottom of each cylinder, they have different pressures. In fact, the right-hand side here has a larger pressure at the bottom compared to the other because the fluid here has a greater depth. Now, kind of moving towards the center, I wonder if I have hopefully you can see my cursor. But let's say we're looking at this point here. Well, at this exact middle point, the left-hand side has a lower pressure than the right-hand side. Well, since the cross-sectional area here, the cross-section of this tube is the same area, then since pressure is force over area, this means that the right-hand side has a larger force compared to the left. Well, that means there's a leftward net force, meaning a leftward acceleration. So if these, so if it's accelerating, it's not at rest, right? At least for more than just a moment. So here, assuming that our water is still, or whatever this fluid is still, then this is not possible. Right, so some implications of that kind of train of thinking is pretty interesting. Right, so what can you say about the pressure at points 1 and point 2 here? Well, the answer here is that the pressures are the same. Right, so the reason is both these containers are open to the atmosphere, so our P naught term is the same for both the left and right hand side here. Assuming that our fluid is at rest, then each of these have the same height, so we're dealing with the same depth, and it's the same fluid, so the same rho. So we have the same pressure at both points. So this implies then that in hydrostatic equilibrium, right, we'll throw in the word equilibrium now, the pressure is the same at all points in a horizontal line through a connected liquid of a single kind. Right, so we do want to make sure that our fluid hasn't changed, right? Because we do need that density term to be the same for whatever 2 points we're looking at. Now, this is a very helpful problem-solving tool for us now. Right? This implies that basically we can use horizontal lines in our diagrams to help us out. Right? So we'll see that in an example.